Good morning, students. We have come to the end of Unit 5. This is the last topic in Unit 5 in Quantum Mechanics 2. So this is about second quantization of Klein-Gordon field. And of course, in this session, we are going to quantize the field. We are going to quantize the complex field. Of course, we know about second quantization very well, and it means that we are going to quantize the field. In the first quantization, we have quantized the particle, and thereby we could obtain the quantized energy. Whereas in the second quantization, we are going to quantize the fields. When you are going to quantize the fields, we are going to obtain the quantization energy of the photon. So it comes under classical fields and second quantization in quantum mechanics 2. And we are going to take only the complex field. The complex field describes the charged system. Therefore, it will describe the charged particles in the quantized theory. And that's why it is necessary to quantize the Klein-Gordon field. And of course, we are going to use the modified Klein-Gordon equation, which leads us to the occurrence of negative probability density. This difficulty can be removed if the Klein-Gordon field phi of x is quantized. That's the reason that we should quantize the field. So in order to remove the negative probability density. However, in general, the field phi of x is complex. And in the previous video lectures, we have been discussing about real scalar fields and complex scalar fields. And we used field operators phi of x, and of course we know that the field operators will have two entities. One is the field function, another one is momentum density operator, and of course both depend on position and time. So we have field operators. Field operators will have two quantities. One is field function, then another one is momentum density operator, and both depend on x and t. We know already. For the real scalar field, we have a photon that will create a particle and antiparticle. So we have only a single photon that will create particle and antiparticle. And using quantization rule, we could obtain the energy of the photon for the real field in the previous video lecture. In the last video lecture in quantum mechanics 2, we discussed about complex scalar fields in which there exists more than two particles. Suppose if there are more than two systems, and we can't judge which particle will have the antiparticle or which antiparticle the corresponding particle, that we do not know, because it contains more than two particles. So we'll have to go only with the complex field at the time. So however, we could obtain the quantization energy of the photon. Now we know that we have used only the modified Klein-Gordon Hamiltonian we used, and we could obtain the energy of the photon. But here we are going to quantize the field in which charged particles are there. So we are going to quantize the charged particles. So with this introduction, let us go into the session. So we are going to consider a complex field. Phi depends on x comma t, which satisfies Klein-Gordon equation. For quantizing the field, let us expand phi 1 and phi 2. So phi 1 and phi 2 stands for field equations phi 1 and phi 2. So for first particle and second particle in terms of creation annihilation operators. As I said earlier, we have field operators in which field functions exist. These field function phi 1 stands for the first field function, and phi 2 stands for the second field function for the second particle. Phi 1 is for the first particle, phi 2 is for the second particle, and corresponding they are connected with the creation annihilation operators. And of course we know that the field function, they are connected with creation and annihilation operators. See here we have creation annihilation operators, and of course they are connected with the plane wave equation also, e power ikx and e power minus ikx. So the field function for the first particle is given by equation 10.134, and the field function for the second particle is given by equation 10.135. These two equations already we studied earlier in real complex fields and real and complex fields, already we discussed. Now these two equations, see here we have equation 10.134 and 10.135, and of course for these two, as I said, these two represent two particles. This is for the first particle and this is for the second particle. Any complex field is described by the field variables as your phi equals phi1 plus I phi2 divided by root 2 and the complex conjugate, so phi star which will be written as phi1 minus I phi2 divided by root 2. The first three slides already we discussed, okay, earlier. So this is just a recall of whatever we have studied for real and complex fields. So now we are going to combine these two, 10.314 equation and 10.135, and substitute here 10.136. We will have this equation for your phi of x and phi dagger of x. So earlier I said phi star. Now as I said, now it is phi dagger because we are going to take the complex conjugate for the operator. So they are all field operators. If it is a function, then we can go with phi star. If it is an operator, always we think about only dagger. So your phi of x becomes equation 10.137. Okay, this is your phi of x, and phi dagger of x is nothing but 10.138. So this is your phi dagger of x, and let ak plus or minus, which is equal to ak1 plus or minus iak2 divided by root 2. The equation 10.137 and 10.138 can be written as. So we are going to combine these two equations using this idea, and we can write your phi of x becomes, look over here, use this term as I said earlier, and in equation 10.137. So this will become plus. Okay, and what is this one? This will become, you are going to take a dagger of the complex conjugate. See here, then this will become minus. So this term will become ak minus dagger, whereas this term will become ak plus. And similarly this term will be a minus, and this term will be, you are going to take the complex conjugate. See here, take the complex conjugate, this will become plus. So this term will become ak plus dagger. Okay, so now you have phi dagger of x, as I said earlier, 1 by root p summation over k 1 by root of 2 omega k. This already we have already studied these equations. Ak minus e power ikx plus ak plus dagger e power minus ikx. So now, as I said earlier, our aim is to find out the quantized energy of the photon. So for which we will have to use quantization rules. The creation and annihilation operators ai dagger and aki, for which the fields phi of I equals 1 comma 2, which they will have to satisfy the following commutation rules. So these rules are here. So aki comma ak j dagger, which is equal to IH cross, provided times del k prime del I comma j equals 1 comma 2 particles, and aki comma akj equals 0, as well aki dagger comma akj dagger commutation, which is equal to 0. Okay, using the above equations one can find out the commutation rules for the field operators too. So your commutation with phi of x comma phi dagger of x, which is equal to IH cross del x minus x prime. Of course we are going to use all the commutation rules. The operators a plus is nothing but a destruction operator for the positively charged particle. A plus dagger is the creation operator for the positively charged particle. Similarly, a minus dagger, see here, a minus dagger is the creation operator. This is creation operator for the negatively charged particle, and ak minus is the destruction destruction operator for the negatively charged particle. So there's a mistake here. We just rectify this one. Okay. The expansion of phi of x in terms of a complete set of orthonormal solutions of Klein-Gordon equation is necessary to quantize phi 1 and phi 2. So our aim is to find out the quantization of phi 1 and phi 1 and phi 2. They are all field operators, and thereby we are going to quantize the charged particles. So that's our aim. In terms of number operators, number operators consist of creation and annihilation operators. So now, in fact, two particles differ in charge, introducing the occupation number operators from this case. So as I said just now, that we are going to use only number operators, nk plus, which is nothing but your a plus dagger a plus. So this is for a positively charged particle, ak minus dagger, ak minus, that will be for a negative charged particle. The above equations, both the equations, turn to be equations of charges. The complex field describes the charge system. Therefore, it will describe the charged particles in the quantized theory. Now, the expression for the total number of charged particles. So we are going to use this equation to quantize the charges. So the total number of charge operators for the complex scalar field is given by this equation. Q, which is equal to IE integration phi dagger phi dot means d phi by dt minus phi dot dagger. Phi dot dagger is nothing but d phi dagger by dt. See here, in right hand side I have given exactly with the explanation, 10.145. Now, as I said earlier, that the field function, which can be written in terms of operators, destruction operators and annihilation operators, as well the plane wave solution. So the plane wave solution of Klein-Gordon equation is given by this formula. Your phi of x equals 1 by root v sigma over k, summation over k, 1 divided by root of 2 omega k, ak plus e power I kx plus ak minus dagger e power minus I kx. Now, we are talking about now kx, which is equal to k mu x mu, 4 dimension. So we will have to include the time coordinate. As I said just now, where phi depends on both x comma t. And similarly, your momentum density operator also depends on x comma t. So your field function phi of x, which can be written in terms of phi of x comma t. Now we will have to change kx as ks minus omega t. So now you just replace wherever you find kx, replace by kx minus omega t. So you are going to replace kx by kx minus omega t. Now the scalar field strength is, look at the scalar field strength, how it changes. Your phi of x comma t, which is equal to 1 by root p summation over k, 1 divided by root of 2 omega k, ak plus e power, see, instead of kx you substitute kx minus omega t. Similarly, right hand side also you have equation 10.147, and as I said, the field operators in equation C 10.145, this is charge operators. So we will have to find out the charge operators. For in the charge operators we have phi dagger d phi by dt and d phi dagger by dt. So we will have to calculate all those things. So that's why I have written equation phi as equation 10.147, and phi dagger, you just take the complex conjugate. So that will give you 1 by root p sigma over 1 divided by 2 omega k a minus you have a plus dagger. And similarly you will have to differentiate equation 10.147 with respect to t. So that will give you phi dot. Phi dot is nothing but d phi by dt. So you will have to differentiate equation 10.147 with respect to t, that will give you minus I omega k. See, you will have to differentiate this. You will have minus I omega k. Here you will have plus I omega k, correct? See, in left hand side you will get minus I omega k, whereas in right hand side you will get plus I omega k. I can pull minus I omega k out so that I can substitute one extra one minus here for the second term in equation 10.149. See here, I have taken 1 minus I omega k out. So I have introduced one minus sign. Similarly, in the equation I need to have phi dot dagger. See here, phi dot dagger, which is nothing but d phi dagger by partial dt. So I will have to differentiate this equation 10.148 with respect to time. So this equation becomes, you will have minus I omega k, but here it will come around plus I omega k, but I will have to pull minus I omega k so that I can introduce one minus sign here. So now I can substitute in this equation to get the charge operators. Now substituting equation 10.147, all the 4 equations, see here 147 to equation 150, see 472 150 in equation 145. So this is equation 145. This is the total charge of the complex field. Now I will get IE divided by, see here, your phi dagger multiplied by phi dot, your phi dagger is here, multiplied by phi dot. See equation 10.48 multiplied by equation 10.149. See here 10.148 multiplied by 10.149. So 1 by root v multiplied by 1 by root will give me 1 by v. Okay, 1 by root 2 omega k divided by 1 by root 2 omega k. See, I have written as 1 by 2 I have pulled out. Then 1 by root of omega k, that another omega k will become omega k prime. See, I repeat, 1 divided by 2 omega k multiplied by 2 omega k prime. I have pulled 2 out. So that will give me IE divided by 2v summation over k prime 1 divided by root of omega k prime. So now look at the first term now. You have phi dagger multiplied by phi dot. So this is your phi dagger and multiplied by your phi dot. And I have pulled this minus I omega k out, common out. And look at the second term, phi multiplied by phi dagger dot. See here, phi dot dagger. So this becomes, your phi is here and d phi dagger by dt is here, and I have pulled one minus I omega out. Already one minus sign is here. See here, one minus sign exists. So I can write this as plus I omega k. See here, I have pulled one minus I omega out. So this will become plus I omega k. One minus sign exists. So this will become plus I omega k. Now you multiply. We will have got to multiply now. The first term with the first term of this, and the first term with the second term of this expression, and similarly the second term of the first one multiply, and we will have the last term with the last term. Now let us see the first term with the first term. So you have a minus a plus, this will become all, these things will become k prime, don't forget. So e power I kx minus omega t multiplied by e power I k prime x minus omega t. Look at the equation now. See here, as I said, a minus a k plus e power I kx minus omega t multiplied by e power I k prime x minus omega t. See, now it's very clear. Now we'll go for the second term, that is first term with the second term. So this will become minus sign. So a minus multiplied by a minus dagger multiplied by e power I kx minus omega t multiplied by e power minus I k prime x minus omega t. See here, the second term with a minus sign. Similarly, you can go for these two terms. See here, these two terms. Similarly, you can go for the last term. So we will get exactly equation pulling minus I omega prime out. Okay, this equation. Now similarly, you will have to multiply with the second term also. You will have to add and multiply. See here. So similarly, I can pull plus I omega k out. So multiplying the first term to first term to second term, then second term with the first term, and second term with the second term. I will have these equations. So it's very simple. Just multiply all the equations. So this equation 10.152. Now I can add these two terms here. You have e power I kx minus omega t, e power I k prime x minus omega t. I can pull I out, and k plus k prime I can pull. See here, I can write this as, see here, e power I k plus k prime, see, out x minus omega t. Similarly for the second term, I can pull here, see, I out, so that will become k minus k prime. See here, k minus k prime minus omega t. Similarly, you can go for the next term. Here minus I, and here it is k prime. So I can write this as minus I k minus k prime. Similarly, the last term will become e power minus I k plus k prime x minus omega t. So this is for the first term. And similarly, you can go for the second term. You can just pull common term out, so that will give you k plus k prime x. Here this will be like this, and this will have similar terms. Now look at the left hand side. Left hand side, I can pull here minus I omega, and here it is plus I omega out. So, but here minus sign is there, here plus sign is there. So what I am going to do is, I can pull minus I omega out and bringing all the terms negative sign. See here, the first term will become negative, this term will become positive, this term will become negative, and this term will become positive. So when you are going to take minus I omega common out, so when you are going to take minus I omega common out, this will give you minus I omega k divided by omega k prime. Now I am going to use the omega k equals omega k prime. The next slide I am going to show. I am going to use omega equals omega k prime using Kronecker delta function. Then I can write this term as omega k square under root, so that will become omega k. I into I square minus 1, already one minus is there, so that will become plus. So plus e by 2. Okay, and this will become omega k divided by omega k, that will get cancelled. So you have e by 2v exists. Okay, now this v also can be removed using this Kronecker delta function. That is, in the previous slide we have the integration. So this is integration over d tau, that you have to remember. So this integration over d tau 1 by v integration over d tau e power I k plus or minus k prime times x, which is equal to 1 by v integration d tau e power minus I k plus or minus it is plus or minus k prime x, that can be written as delta function of x plus or minus k prime, provided k equals plus or minus k prime and omega equals omega k prime. So now the equation 10.153 becomes 10.155. Is it okay? Now we will see one by one. As I said just now, here you just take the first term. I will deal with the first term easily. Now the first term will be ak minus ak prime plus this term. Now here, using Kronecker delta function, that will give you k equals minus k. See here, k equals minus k prime. So instead of k prime you substitute minus k here, and in the next term k equals plus k prime. So instead of k prime you substitute plus k. Now this term, look at this term, k equals k prime. So instead of k prime you substitute k. Here k equals minus k prime. So instead of k prime you substitute minus k. So here in the operator, so this will become, see here, as I said, your first term becomes ak minus, and here it is a minus k plus. See here, you just look at the first term, k equals minus k prime. So wherever you find k prime, you have to substitute minus k. See here, you have minus k. And other terms, look at the next term, k equals k prime. So k prime become k itself. Here also k prime becomes k itself. But here in the last equation we have k equals minus k prime. So wherever you find k prime, you have to substitute minus k. So the last term. And as I said earlier, we are going to pull minus I omega k out. So this will become plus sign, this will become minus sign, minus, plus. So you have, see here, you have minus sign, plus sign, minus sign, plus sign. And also the same argument for k equals, say, minus k prime. For example, you just take the first term, k equals minus k prime, and your k prime becomes minus k. Look at this one, see here, k prime becomes minus k. So similarly you can get equation 10.155 for all the rest of the terms. Is it any doubt? Maybe. Okay, we will go to the next one. Now I have written the same equation now. See here, e by 2, the same equation I have written. Now I am going to simplify using commutation rules. You just take the first two terms. It is exactly resembles with AB minus BA. commutation with AB minus BA, that will give you commutation of A comma B. See here, AB minus BA will give you commutation of A comma B, which is equal to 0. So the first two terms, see here, first two terms, these terms, they will get cancelled. They will become 0. The first term in this equation and the first term of this equation, they will get cancelled. Similarly, you just take the last two equations. See here, this term and this term. You have A, B, this term will be minus BA. Look at these two terms. Again, AB minus BA will give you commutation of A comma B, that also will become 0. So this term will become 0, as well this term will become 0 here. Now we'll go for this term, okay, second term. Second term, you look at the second term can be written as AK minus dagger, which is equal to AK minus dagger, AK minus plus 1. We can use this formula. Similarly, AK plus dagger can be written as AK plus dagger, AK plus 1. So we are going to substitute for this one. We are going to substitute for this term as this one. And already one minus is there. So I am going to write this term as minus of minus. Here you have minus. The same term I have written as minus AK minus dagger. See here, AK minus dagger, AK minus, instead of plus 1, minus exists. So that's why I have written minus 1 here. Next term I have written as it is. Okay. Now this term A plus dagger can be written as A plus dagger, A plus 1. See, plus 1 I have written. The last term, the next term, I have written as it is, minus AK minus dagger, AK minus. Now minus 1 and plus 1 will get cancelled. And I am going to combine these two terms. See, I am going to combine these two terms, and I can write this as twice of this term, 2 times of AK plus dagger, AK plus. And I am going to combine the first term and the last term. See, first term and the last term. And I can write this as minus 2 AK minus dagger, AK minus. And these two terms, see here, you have AK plus dagger, AK plus, that is known as NK plus. That is for the positively charged particle, number operator for the positively charged particle. And what is the second term? AK minus dagger, AK minus, this is for the negatively charged particle. I can represent this as AK minus. So equation 10.149 can be simplified as the total charge of the system, Q, which is equal to E times summation over K, NK plus minus NK minus. So equation 10.160 represents the total charge in terms of number operators. So as I said earlier, and NK plus stands for a positively charged particle, NK minus goes with for a negatively charged particle. The above equations turn out to be equation of charges. The complex field describes the charge system. Therefore, it will describe the charged particles in the quantized theory. Now, the eigenvalue of Q, the total charge system, is given by Q equals E times, there are number operators. So we can write, instead of capital N, you can write, see here, instead of capital N plus, you can write small n plus. So there are numbers. So that's why you can find out the eigenvalue of Q, which is given as equation 10.161, which is n plus minus n minus, where n plus and n minus both go with 1, 2, 3 up to infinity. And of course, where A plus is nothing but annihilation operator, and A plus dagger is nothing but your creation operator, and n plus n minus are number operators. This is for the positively charged particle and this is for the negatively charged particle. Thus the Hamiltonian and total charge operators are expressed in terms of number operators. So Hamiltonian, already we have quantized to find out the quantized energy of the photon. We have used the Hamiltonian equation. Can you remember? In real and scalar fields. So they are expressed in terms of number operators. Here now we have used in terms of number operators to calculate the charge operators. Hence they are all diagonal elements. See, one can also obtain the Hamiltonian momentum density, also you can obtain momentum, and the total charge operators. The positively or negatively charged particles have identical properties except the sign of their charges. You have plus and minus, that's all. So to conclude, in relativistic quantum field theory, every charged particle is accompanied by an antiparticle having opposite charge. So this is a general result in the field theory. Examples of particle-antiparticle pair are the charged pi plus and pi minus particles, k plus and k minus particles, and so on. The charge in question may be either electric charge or some other conserved quantum number like strangeness or hypercharge. The electrically neutral K0 meson has an antiparticle k bar naught, which is also electrically neutral. So these two particles carry opposite hypercharges. So in this session we have quantized the total charged particles. We have quantized, and we have used field equation, field operators, field functions. So we have used, and with this unit 5 we are going to end up quantum mechanics 2. And thank you for your all cooperation, students. Thank you so much. Bye, students. Let us see in the next time.